Hello everyone. Today let's solve the problem number 1631, path with the minimum effort. Right. So let's see what the question states here. Let's come to the example one here. Yep. So this is fine. Yeah, we are given a grid of heights. You can clearly see here. We are given grid of heights, right? So they have given us a wonderful diagram as well here. We are given grid of heights. We can move up, down, left or right. So we can move up, down, left or right. Yep. So we can move up, down, left or right. The effort of a path is the maximum absolute height difference. The effort of the path is the maximum absolute height difference between the consecutive cells. See, again, the effort of the path is nothing but the maximum absolute difference, height difference between the consecutive cells. Yep. So we must reach the bottom right cell, this one. We must reach the bottom right cell from the top left cell. From the top left cell, from here, we have to reach here from 1 to 5, right? Accordingly with the question. So we must reach the bottom right cell from the top left cell with the minimum possible effort, with the minimum possible effort. So then what we need to return? We have to return that minimum effort value, that we have to return the minimum effort value. Yep. So this is fine. This is fine, I believe. So see, so heights we have been given 1, 2, 2, 3, 8, 2, the row values actually, and 5, 3, 5 finally. The output here is 2 because the root of 1, 3, 5, 3, 5. So see here, this one 1, 3, 5, 3, 5 has the maximum absolute difference of 2 in the consecutive cell. See here, 1 minus 3 actually it will lead to minus 2. So this one, the next one minus the current one will be uh, doing actually 3 minus 1 2, 5 minus 3 2 again. So here this one will go with left, this one current cell minus the previous one actually when we are considering row actually, right? Current cell minus the next one actually, sorry, 5 minus 3 and this one 3 minus 5, it will give us 2 itself, right? So here the root of 13535 has the maximum absolute difference of 2 in the consecutive cells. So this is better than the root of 12225. So this one also we can just go 1 2 2. So this path they are saying actually 1 triple two five, right? So this one we are having the absolute difference of basically one here, right? So finally, yeah, one actually until here. See, so this one we will consider until here, right? So this one. So here, let me remove this one. Don't consider this one until here. Absolute path we have is one actually, right? Two minus one. Uh, this one 2 minus 2 will be 0 actually. 2 minus 2 again it will be 0, right? So this is better than this one. 1 then 0 0 0 then this is 2, right? Absolute path difference we have is 2, right? So first one is the better one actually in this case, where the maximum absolute difference is 3, right? So this one we have the maximum absolute difference 3. The maximum here 5 minus 2, that will lead to 3, right? So maximum absolute difference we have is 3, and maximum absolute difference for this one we have is 2. So we will consider all the things: 3 minus 1, 5 minus 3, 3 minus 5, and 5 minus 3, and again this one 3 minus 5. The maximum of all the numbers that we'll consider, we will get the maximum absolute difference, this one 2, for this path, right? So for this one, 1 triple two five, we will be going with a 1, sorry, yeah, 1 minus 2, 1, this one, 1, 0, 0, and 3, right? So 3 will be the absolute path, right? So this is fine. Yeah, same thing goes with the example 2 as well. Example 2 and example 3 as well. Yeah. So you can just look it in the same way, look at it in the same way, or you can just implement it in the same way. Right. So now, before hopping into the approach part, let me tell you one thing. So we can solve this problem using the Dijkstra, right? We can solve this problem using the Dijkstra actually, right? Dijkstra's algorithm, if you know, we'll be implementing the same thing. So we'll be making use of the Dijkstra's algorithm here, right? Since we need the minimum maximum edge weight path, right? Each cell, we can just consider each cell as a node, and the edge cost is the height difference. Edge cost is the height difference. Now let's see this one step by step. Let's move on with the approach part. Actually, let's consider the same first example that they have given in the question, right? So let's go with this example itself. Yeah. So this is simple to understand. Actually, let's go with the first example itself. So just give me a second here. Yep. This one itself. So one second. Yeah, as I've said, we'll be going with the Dijkstra, right? So if you don't know the Dijkstra's algorithm, you can just go through the graph-based this one algorithms playlist, and you have the Dijkstra algorithm there. You can just look at the video, and then you can come back, right? So we will understand this one better. You can just solve this one very easily. The algorithm is quite easy. I'm not gonna lie. Dijkstra's algorithm is easy. It uses priority queue. We know this one, right? Dijkstra's algorithm quite obviously uses the priority queue to solve the problem. Yep. So um, usually we'll be making use of the Dijkstra when we are not given the negative weights, when we are not dealing with the negative weights, right? So we don't have the negative weights. Accordingly with what we discussed actually, and we can easily go with the Dijkstra as we are given this one two edges. Along with the two edges we are given weights actually. Yep. So this is fine. We just discussed we'll be making use of the Dijkstra's algorithm since we need the minimum maximum edge weight path. Each cell is a node here, right? Each cell is a node. The edge cost is the height difference itself is the edge cost, right? Height difference is itself is the edge cost, in the sense that is nothing but the weight actually, right? Usually we'll be going with the two nodes u and v, and w nothing but the weight. Here w is nothing but the edge cost, right? Edge cost is the height difference. Height difference is nothing but the weight here, also known as edge cost, right? So this is fine. Next, let's move on with the this one uh, approach part. So let's consider the same example for the approach here. So the first step here will start from 0 comma 0. So this is 0 0, this is 0 comma 1. So let me mention this one quickly. 0 comma 2, 1 comma 0, 1 comma 1, 1 comma 2. So this is 2 comma 0, 2 comma 1. So this is 2 comma 2. Yeah, we'll start from 0 comma 0. So this one, this cell actually, right? So initially we'll start from 0 comma 0, and effort is 0, and effort is 0, right? And effort is 0. Then let's move on with the second step here. Second step, we will move to the neighbors, right? So neighbor, let's move to this one right side, 0 comma 1 actually. 0 comma 1, we have the value 2. We have the value 2, and difference is 1 to the previous cell, and the difference is 1 actually, right? So and we will move to the 1 comma 0. Also this is also the neighbor, right? So we can just move one step right or down. Left we don't have any cell, up also we don't have any cell, right? So next we'll go to this one. What do we call? This is 0 comma 1. Next we'll go to 1 comma 0. 1 comma 0, the value we have here is 3, and difference is 2. Nothing, 3 minus 1 will give us 2, right? So difference is 2. We'll choose the smaller effort first, like similar to this one. We'll choose the smaller effort actually, right? A smaller effort first actually, right? So this is fine. So I'll just go with the, let's move on with the third step here. We will keep updating the each cell's minimum effort, right? Maximum of path so far, and new difference similar to this one every step, right? Every step. So we'll continue until reaching 2 comma 2. We'll continue this until reaching 2 comma 2, nothing but 5, right? So final minimum effort would lead to 2. Final minimum effort would lead to 2 actually, right? So the output that we got here is 2, which is equivalent to the output that they have mentioned for example 1 within the question, right? So our approach works absolutely correct here. As we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. Yeah. So what will be the time complexity here? The time complexity would lead to because of n into m into this one, logarithmic n into m. So why it is n into m into logarithmic n into m? Basically each cell is pushed into the priority queue at most once, right? Each cell is pushed into the priority queue at most once. So the time complexity would lead to because of n into m into log n into m respectively, right? So what would be the space complexity here? Space complexity would lead to because of n into m, right? So space complexity would be because of n into m, because we'll be making use of the distance matrix and the priority queue. Dijkstra's uses priority queue, right? So we'll be going with the distance matrix as well. So overall space complexity would lead to because of n into m. So the time complexity and the space complexity for the code that we'll be writing in the future would be because of n into m into logarithmic n into m, and because of n into m respectively, right? So now as we are completely familiar with the approach as well as the complexities part, we are good to write the code. Let's start writing the code. So the first step here would be, uh, let's we'll be making use of the length of the height, this one. Rows and columns we have to go with, right? So let's do one thing. Let's let me assign this one to the variable n. I'll just go with the rows first. So this will be heights dot length. Next columns, I'll just go with m here. So this is nothing but heights of 0 dot length. So this is fine. The next step would be, let's go with the directions. So as they have mentioned, up, down, left, or right. So I'll just go with dx here. Yep. So this one will be minus 1, 1, 0, 0. Let's go with the dy this time. So this one will be minus 1. Sorry, we are dealing with a column, right? So it has to be 0, 0, minus 1, minus 1. Yeah, neighboring, no neighboring column. So let's go with the min heap or the min priority queue, storing effort, comma x, comma y, right? I'll just go with the priority queue here, priority queue. So this will be int. So let me go with the variable pq. So this one will be new priority queue. Yeah, new priority. So this is fine. New priority queue. New priority queue. Right. So this is fine. 1 second. So next, what shall we do? I'll just go with here a comma b. So this is fine. I'll just go with a of 0 as b of 0. Yep. So this is fine. Next step, what we'll be doing, let's go with the distance matrix to store the minimum effort to each cell. Right, so I'll just go with here distance. So this one will be new int of n and m respectively, n and m respectively. Next, let's go with a simple for loop. So this one will be int row of distance. Uh, this one will be arrays dot fill of, let me pass the row, and let me go with integer dot max value, right? So I'll just go with max value. This is fine. Yep. So the next step would be, let's start from the top left one. So I'll just go with the distance of 0, 0. Initially we have to start with a cell 0, 0, right? So I'll just go with a distance of 0, 0. This is fine. Next, let me go with of a operation that is provided by the queue, priority queue actually. New int, let me pass here 0, comma 0, comma 0 initially. Yep, so this is fine. So let me come out of this one entirely. Now let's go with a standardized, this one, priority queue while loop actually. This one while dot of pq dot is empty as usual. So didn't I keep parenthesis here? 1 second. So within the while loop, the first step would be, so let me assign current to the pq dot pole. Yep. This is fine. Int, let me go with effort. So this one will be current of 0. Yeah. Let me assign x to current of 1. Then finally y to current of. Yep. So this is fine. Next step, if we have already reached the destination, then we have to return the effort, right? So let's write the simple if condition here. If x equals n minus 1 and y equals m minus 1, then we have to return effort, right? We have to return effort. Yeah. So let's go with this one. We have to skip if already found smaller effort, right? So if effort, if it is greater than dist of this one x, y, then what we have to do? Let me skip. So for skipping, I'll just make use of the continue keyword here. So we have to explore all the four directions. So let me go with for loop here. So this one in equals 0, I less than 4, because we are starting from the 0, right? So we have only four directions, up, down, left, and right. I has to be less than 4. I plus plus. So yep. So within this for loop, first thing, I'll just go with int nx neighboring x. So this one will be x plus dx of I, quite obviously, and consider ny as well. So this one will be y plus dy of I. This is fine. This is clear. Next, let's do one thing. Let's go with a boundary check, right? So let me write the simple if condition. So nx neighboring x, it shouldn't be less than 0, or ny, it shouldn't be less than 0 as well. Next, nx, it shouldn't be greater than or equal to n, yeah, or ny, it shouldn't be greater than or equal to m. Yep. So then let me give continue, or we have to skip. In that case, I'll just give the continue keyword here. Next, we have to calculate the new effort, right? So I'll just go with here int diff equals, I'll just go with math dot absolute. This one will be heights of x and y. So this is fine, minus heights of this one nx and ny, right? So this is fine, man. Yeah, now I'll just go with new effort. We go with math dot max of, let me pass effort. Along with the effort, let me go with diff. Yeah, this is fine, man. So final one is, if the new effort is smaller, then we have to update and push to heap, right? So if a simple one here, new effort, if it is less than dist of nx and ny, so this is fine. Then I'll just go with the dist of nx, ny. Let me assign this one to the new effort actually. Yep, so this is fine. So then let me go with pq dot offer operation here, offer operation here. So this one will be new int. Yep. So I'll just go with new effort. So this one, let me set this one to the capital E. Somewhere did I use this one somewhere? No, right? So this one, 1 second. Yeah, here I have given capital E itself. Yeah, this one. So this one will be new effort, comma, nx and ny, neighboring x, neighboring y. So this is fine. Yeah, let me come out of this one entirely. Yep. So now we are left with only one step. So we have to return 0 if it's not possible, right? So we'll never reach here, not to worry, right? So let me format the code once and let me hit the run button. So let me format this one. Why this is not getting formatted? Yeah, let me hit the run button, man. Anyways, we have some errors here. Huh? 1 second. Oh, this one new effort actually. Where is this line number 35? Let me run this one again. Wrong answer. Expected to output that we got here is 0. This one also wrong answer. For the case 3, we are getting fine. For everything, we are getting 0 itself. Okay, somewhere we have done something wrong. Let's check. So maybe I have done something wrong within the direction actually. So this one, yeah, let me remove this one. I make this mistake most of the times actually. Let me remove the -1 actually. So this one has to be -1 and +1. Yeah. So let me hit the run button again. Now this has to work. Let's see. Yeah, the sample test cases are getting passed. So let me hit the submit button. So I hope this works for all the test cases. Yeah. So Dijkstra's algorithm works absolutely fine here. So if you know the Dijkstra's algorithm, the implementation will be very easy, man. Yeah. So if you would have solved the Dijkstra's algo, the problems based on Dijkstra's algorithm, or if you know the Dijkstra's algorithm, that's well and fine. You can solve this problem, or you can implement that one quite easily here, right? So this is fine. We are done with the problem. Yeah, we are done with the problem. Basically, whatever the code that we have written works absolutely correct for all the test cases. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.